Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. Problem number 174 today, the dungeon game. We're doing another hard one, and this one is it's not too popular. Google and Bloomberg are asking it, or they have recently. I thought it was a decent problem nonetheless to go over, so I hope you guys enjoy it. With that said, if you haven't tried it already, pause the video, give it a shot as always. But here we go. There is no but. Let's just dive into it. We're told that demons have captured the princess and imprisoned her in the bottom right corner of a dungeon. The dungeon consists of an M by N rooms laid out in a 2D grid. Our valiant knight was initially positioned in the top left room, and he must fight his way through the dungeon to rescue the princess. Okay, so he's starting up here in the top left. We got to get him down here. Fine. It says that he has an initial health point represented by some positive integer. If at any point his health drops 2 or below 0, 0 or below, he immediately dies. Okay, so it can't hit 0, it can't hit below 0. Some of the rooms are guarded by demons, so the knight loses health upon entering these rooms. Others are empty. Others contain magic orbs that increase his health. Okay, in order to reach the princess as quickly as possible, the knight decides to move only rightward or downward in each step. We need to write a function to determine the knight's minimum initial health so that he is able to rescue the princess. For instance, here we're told the minimum he needs is 7. And the reason he needs 7 is because once he steps into this first room, he loses 2 points. So he's at 5 now. Okay, keep it up here at 5. He loses 3 more, and that gets him to 2. He gains 3, which gets him to 5. Gains 1 more, so he's going right, down, right? This is the optimal path. So right. He gains 1 more, he's at 6. Then he's going to lose 5 in his final step, so he's down to 1. And that's why he passes. So we need 1 to end off, at least. We said it can't drop to 0 or below. In terms of notes, we're just told that the knight, this health has no upper bound. Any room can contain threats or power-ups, even the first room and the bottom right room. Okay, so as we saw, these can both be negative or positive. I think the question makes sense. And so how do we actually approach it? So what we can start with thinking about here is to actually ask ourselves, at any given point along the path that we're creating, how much health would we need before taking a step on a given cell? So let me paint it out this way. Let's say we recreate this grid, and I'll make it also an M by N grid, and we'll keep it blank for now, and I'll call it HP for health points. We'll stick with the standard video game nomenclature. And what we want to know is the following. Is for me to be able to stand on any given point, I need to know how many health points I would need before stepping on that grid. And what I mean by that is this. If I was to step on the grid, if I'm the knight, I would lose 2 points. That means to stand on here, I would need a minimum of 3 going into that step. I would say I need to have 3 health points and then step on this grid because I know I'm going to be down to 1 after this. All right. So we then ask ourselves, I start with 3 health points. After I step here though, I'm going to be down to 1. Okay. So this 3 is going to go down to 1. And now can I go here or here? Well, the answer is no, because if I step down to 1 and then I go to this 3, I would go from 1 to, I'd lose 3, then I'd be at -2. So that's not going to be enough. So I can try my luck down here and say, well, let me try to take a step down then and say, well, if I go down, I'll lose 5 points. And then, wait, now I'm going to be at -4 points. And so that's not enough. And so I can't go right. I can't go down. So 3 points must not be enough. Okay, so maybe we choose to take the lesser of the 2 evils and we say, okay, well, to step here on this grid, I would need 4 points. Okay, and that means I would need 3. I knew I needed 3 points here to kind of step here before. But if I have 3 points, then I step here, I'm going to lose 2. That's going to bring me down to 1. So I need to have enough so that even if I lose 2, I can make it to my next point. Well, if I was to lose 2 after standing here, and I want to go to the right after and I need 4, then I would need 6 here. Because I'd say, okay, if I've got 6 and I stand right here, I lose 2, that gets me to 4. From 4, I go here to this point, and that's going to lose me 3 more, so I'm going to be down to 1. And that's okay. So I'm so far so good. And then, maybe we take a step here, and we realize, well, okay, so I'll be good. Like I can make it here with, how many points would I need to make it here? Well, I need at the very least 1 here. If I step here with 1 point, I know I'll gain 3 more, so that'll get me to 4. And then, I can keep walking down. I step down here. That'll get me to 5 total points. But then, wait, from 5, once I step down here to the bottom, I'm going to lose it all. So I'm going to go down to 0, and that's not good because then I've died at the end. Okay, so now we got to take a bunch of steps back and reverse the work we've done. And so the reason I'm describing this first approach is this is what a top-down recursive approach might look like to this problem, where you say, let me pick every possible path and ask myself, what would my total health be along the way as I go, and how much would I need to survive? And if I check every single one of these paths, I pick the one that would require kind of the minimum amount here. Maybe would have the lowest, not the lowest loss at any given point, because we'd have to try every single path. And so in order to to make this top-down recursion method work, this will take a very, very long time, and it wouldn't be a very effective approach for a couple of reasons. One is the fact that there are certain steps along the way that we would be recalculating. Okay, so there's some repeated calculations. The second part of it is the fact that, well, there's some not overlap, but there are sub-problems happening here. And such that if I kind of want to solve this entire problem, if I want to solve this entire problem here on how to get to the end, that requires me to solve a smaller problem, which maybe looks like this, or a smaller one that involves solving this, or really smaller and smaller chunks along the way. Basically, what I'm hinting at is the fact that there are overlapping subproblems, or they're overlapping subproblems, and the second is that there is a optimal substructure, meaning that if I solve a smaller problem, then I can get to a slightly bigger problem, which will help me solve a slightly bigger one, which will eventually get me down to the end. I'm using this build-up to basically explain what the logic is, how we get to the point where we realize that this is in fact a dynamic programming problem. And so typically with dynamic programming problems, what we need to do is to understand what would the top-down recursion solution look like, the top-down recursive solution, what would that look like? And then how can we do something to make it more efficient? Namely, to memoize it, for example, which just means let's store the values we've calculated and maybe find a way to work either from the top down or bottom up. And an approach like this here, I've done other videos like this, and I'll link them down below. I think the one that I did, which was similar, was least steps from source to target or something like that. Again, I will link it down below, but this is going to be a very common trick that you'll see repeated in different DP problems, where we can recreate a grid of the size that we've got in our input, and then see if there's a way to work backwards to find the actual optimal solution on how we get from here to here. By finding a way to solve, maybe what do we need? How do I solve my final step? What do I need at the very minimum at my final step, and then work backwards from there toward the solution. So let's think about it this way. If I'm looking at this problem and I want to take this approach, I realize, okay, there's a way we can kind of memorize this. Now I want to try to work backwards. I'm going to ask myself, how many health points do I need before stepping on any single cell? So I'm going to look at the end right over here. And I'm going to tell myself, okay, if I step on this cell, I know that I'm going to lose 5 health points. If I'm going to lose 5 health points by standing here, I'm by default going to need, or by definition, I'm going to need 6 health points before I step on this grid. The reason I'm going to need 6 health points is because once I stand on it, that'll bring me down to 1. If I had only 5 health points here and I lost 5, that'll bring me down to 0 and I'd die, and we don't want that because that means no more baby bear videos. So that's why we're going to need 6 to stand here. Okay, so that's fine. We know in our decision-making model here within this question, we can only go right and we can go down. Since at any given point we can make one of those 2 decisions, what I like to do with these questions is to say, let me solve the rightmost column and let me solve the bottommost row, because in these, there's only one way to go. Anywhere in this column, I can only go down. Anywhere in this row, I can only go to the right. I can't go down, right? And from here, I can't go right at all. So I'm going to ask myself, let's say I was taking the straight path down, what would that look like? Well, I know I need 6 points to get here. If I was to stand on this grid, what would happen to me? Well, I would gain 1 health point. If I were to gain 1 health point, and I know that to get down here, I need to get to 6, well, what that means is I surely would be okay with having 5 health points here. Okay, if I had 5 health points and I stepped on this grid, or this cell here, I stepped on here, I would gain an extra 1. That means that when I got to here, I would have the 6 that I needed, and so I win. By similar logic, we can also conclude that we would need 2 health points here at this cell. if I was to step on this cell with 2 health points, oops, I would gain 3 points. Okay, I would gain 3 health points here. So I did some business over here. If I ended up with 2 health points, I would gain an extra 3. That would get me to 5. From here, I'd gain an extra 1, which would get me to 6, and I know 6 is what I need. This is how I'm working backwards to fill this in. Let's do the same thing over here, and then we'll fill the rest of it. Now, if I step on this grid, I know I'm going to get 30 health points. Okay, that's wicked. I know I'm going to get 30 health points. So hypothetically, then maybe I think to myself, okay, well, I can be at like negative 24 here. Well, if I have negative 24 health points and then I get these 30, then that's going to bring me to 6, and that's good. That's what we need. Unfortunately, the issue is if we were to have negative 24 health points here, we would have been dead. So not only can we not necessarily, we can't get it to 24, we need to have at a minimum of 1 at any given point. So that means this is going to be 1. It's not going to be this value, it's not going to be this value minus the preceding benefit that we'd get. So let's think about how that differs from the approach here. Notice that if we get positive health points, right? So we have positive health points here, and we got positive health points here. If the amount that I need, 6, minus whatever my benefit is greater than 0, then I'm just going to subtract them. I say, okay, I'm not going to be too greedy here, not to be confused with a greedy approach, but I'm just going to need this 1 health point, so 5 will be enough here. However, even though I know I'm going to get 30 points by stepping here, I can't just say, well, I need 6 in my next step, so just take away 30, and then we'll be good. We'll get to 6, because if at any point along here, any of my health points are below 0, I die, and we can't have them, all right? By similar token, I can also tell myself, well, if I step here, I somehow get to this position, I'd get 10 health points, and I know that I need only 1 to get here, so maybe I'm tempted to just say I need negative 9 if I was to step here. Again, this is no good because I would be in a negative here, and then I'd die. This HP table right over here represents what the minimum health points we need at any given time. The minimum here for this step, oops, is not negative 9. Okay, negative 9 is not the minimum. That's not a valid minimum. Sorry, I lost. There we go. All right, so we're at the 1. So no matter what, if for me to step on any one of these, this is the number of health points that I need for it to be a valid step. All right. Now, let's look at this one. Now, this one gets interesting because this is the first time we are losing, right? Apart from this beginning here, or the end, I guess. This is the first time where we're losing health points by stepping on a grid. Okay. So what do I do here? If I step here, I will lose 10 points. I know that from here, I need to get to either here. I can take a step right to get to the 5, or I can take a step down to get to the 1. All right. So no matter how many health points I have here, once I step on it, I will then lose 10. My argument here that I'm going to make, and we're going to see this reflected in the code, is that I would then need a minimum of 11 health points before stepping on this grid. The reason I need 11 before stepping on this grid is because if I have 11, I step on it, I will lose 10. This will get me to 1 health point. However, with my 1 health point, I know I can go down here. And at that point, I'm good with the 1 because I know I can make it to the end. We've already determined that on our calculation here. If I was to have gone right, I would have needed 15 health points because I would step on this grid here, or this cell with 15 health points. I'd lose 10. That would get me to 5, and 5 would be enough to go over here. However, we're looking to solve for the minimum health points required. So what I did was I said, let me take the absolute value of this number, the 10 that I'm going to lose, and I need to add it to whatever the smaller is of my 2 options. My 2 options are either below me or to the right of me, and that's how I've landed with this 11. Let's take the same logic over here. If I step on this grid, or this cell, keep mixing those up, I'm going to lose 5 points of health. If I want to get down here, I need to have at least 1 point. This means that 6 points should do the trick. I step here, I lose 5, that gets me to 1. I step down here, but I'm good. All I needed was 1, so we're all happy. Because from here, I'd gain 10, I'd gain 30, then I'd lose 5, but we're not concerned about the loss because I really have enough health points. My other option was to say, I could also take 17, lose the 5. Oh, I don't think that's math. 16, lose the 5, gets me to 11, then I can go here. However, the reason I'm not going with 16 and I'm going with 6 is because we're looking for the minimum health required at any given step. I'm going to fill in these last two right over here. This -3 here tells me I'm going to lose 3 points when I step here. Which is smaller, a step to the right or a step down? A step to the right is smaller. So I'm going to need to have 3 extra points to offset this loss here, meaning I will need 5 health points in order to stand here. Okay? Again, if I was to go down to the 11, I would have needed 14. 14, I would lose 3 by going down. Right? Once I step here, I lose 3. So, but since 5 is smaller than 14, we're looking for the minimum. I'm going with 5. Finally, by the same token of logic, we get to the end here, and we can conclude that 7 would be the amount of health points we need. Once I step here with 7 points, I will lose 2 by default. So I'll have 5. But I've noticed that I'm good. If I can make it to here with 5, I've solved the whole problem. If I can make it to here with 6, I've also solved the whole problem. However, to get to 6, I would need 8 health points here, not the 7. That's why we're going with the 7. It's the smaller of the two in terms of halves. For me to win this game, to get to the end, this table tells me at any given point how many health points I would need to have, right? That's what we've actually solved for here. If I was to say, if I somehow make it to here with 11 points, I win. Okay, I can actually solve this problem. If I somehow make it to here with 6 points, I win. If I somehow make it here with 2 health points, I win. Since we chose the minimum optimal option at every given point, we will kind of conclude that if we were to fill this in backwards, then 7 would be the optimal and lowest amount of health that I need to get through this. So that's the manual walkthrough of how we'd actually go about filling in this grid. The code's going to reflect the exact same thing. The code is a bit lengthy, but it's not, I'd argue it's not too complicated. And I think we're in a position where we can dive in and see how we'll fill the code in to get this table the way we want it. Let me know down below if this explanation helped, if it made sense. If not, of course, as always, drop a comment, and I'm happy to clarify any confusion you may have. So we'll take a look at the code here. I'll move this over. Since we're not given any constraints on whether or not the board will be valid, I'll start by doing some error checking. After the error checking, we will create our HP table. And then what I'll do is I'll fill in the table for the right column and bottom row as I did manually. So I'll say fill right column, fill bottom row. Then we'll fill the rest of the table. And then finally, we will return our final answer, which is just return. I'll call the table HP, and we'll fill that initial entry. So for the error checking, we'll do something as simple as, if not dungeon, if we're just given an empty entry, we're going to return, what do we want to return? We want to return the minimum health, so I guess 0 or none. Again, this is something you can clarify with your interviewer at the time of your interview. Now we want to create the actual table, and it'll be of the same size n by n. So I'll call it HP, and what I'll do is we will say, so we'll create a row for some variable in the range of the length of dungeon. So actually maybe I'll call this R for every row, and then we'll say we want to fill it with, what do we want to fill it with? We can just fill it with zeros to begin with. We'll fill it with 0 for some variable, we'll call it C per column, in the range of the length of each row, dungeon R, just like that. And so what this will do is just create this m by n grid for us. The first number I'm interested in filling, and actually even before I fill these two, will be this bottom right corner over here, right? So this one that we filled right here. And how I'm going to do that is as follows. I'm going to say that HP -1, -1, so the final entry, it's going to equal, let's think about this, it will have to equal 1 if we have a positive number, okay? So it'll equal 1 if the dungeon's final cell, if it's greater than 0, okay? And why we say that is because imagine this was a 5 instead of a -5, okay? Well, I wouldn't need any more than 1 health point if I was landing here and I knew I had a positive value to kind of augment on what I already had. Otherwise, if we have a negative number, like we did right here, where we had a -5, I knew that I needed -5, the absolute value of that rather, 5 plus 1, because I'm going to lose the 5 here. So I would have to take the absolute value of dungeon -1, -1, plus 1, okay? And in this case of, the -5, I knew I needed 6 when I come to that I come down to that spot. And so that's why we took the absolute value here and added 1. So this is going to be our initial setup. If I was to kind of draw this out, it would look like imagine this was a kind of an array with the 0, 0, 0, 0, 0, 0, 0, 0, and in this case here, I guess it would be a 6. That's kind of all that we've built so far. Now, I want to fill that rightmost column. So what I'm going to do is I'm going to pick every row, starting from the second last row. So we'll say for R in range, in the length of HP minus 2, so minus 1 would put me at the last row. I want to have the second last row, and I want to go upwards. And from here, what I want to do is the following. I want to say that if let's think here, if dungeon at the row that we're at, and -1 is going to represent the final, or the rightmost column, if that number is greater than 0, okay, and what we'll do is the following. So if that number is greater than 0 in the actual dungeon, then that means that by stepping on this, I will gain health points. And so if I gain health points, that means that HP of our -1 would equal however many points we need down below minus the value that we have that we're going to earn. So for example, when I saw right here that we were going to earn 1 point, I just said, okay, cool. So that means that to be here, I'm going to need to take this 6 points and just, I'll take 1 less than that. Since if I stand here, I know I'm going to gain 1 point. That'll get me to the value I need here. So I'll say 6 minus 1 is 5. So I'll say that would equal HP of R plus 1, -1. Now, that value minus the value that I'm at. And so maybe what I'll do is I'll say cell is equal to dungeon, since I'm going to use this a couple times. I'll say if the dungeon cell is greater than 0, then I can subtract the value of that cell. However, what I'm going to need to do is one more caveat here, where think about what we did here. In this case, cell was definitely positive, but if I took 6 minus 30, I said that would get me in trouble because I'd get a negative number. And so we were always bounded to having at least this 1 here. And so what I'll do is I'm going to take the maximum of this subtraction that we had and the value of 1. Okay? The reason we're doing this maximum, again, is think about what we did in this scenario versus in this scenario over here. That's why I'm taking the maximum of the two. Otherwise, if the cell is negative, so maybe I'll spell out the logic here fully. So I'll say if cell is less than or equal to 0, then we'll do the following. We'll say that HP of R -1 is equal to, well, if we know we're going to lose points like we did here, right? We said that we had to take the absolute value of 10 and add it to the minimum of the right and down below. Okay, we have to take the absolute value of the cell. We have to take the absolute value of the cell plus the minimum of its right element and its lower element. However, since we're filling the first column, all we can really do is take the absolute value and add it to the item below. And so I'm going to look at my notes here quickly to make sure that I didn't mess that up. And so what we do is, like I said, I'd have to take the row below, so HP of R plus 1, -1, and add to it this amount that we would be losing. So in this case, I'm not comparing what's to the right and what's below me already, since I'm in the rightmost column. We will be doing that though when we're filling the rest of the table. The logic here is pretty similar, so I'll skip ahead just a bit. I'll say for every column in the range of, I guess this would be the length of HP -1, so the bottom row, and we don't want to start from the last column, which would be -1, we want it at -2. And we want to decrease by 1 every time, so we're going to go leftwards. I'll say the same thing, where we'll say cell is equal to dungeon at -1c, and we'll tell ourselves if the cell is equal, if the cell is greater than 0, then we'll say that HP of -1c is going to equal the maximum of the table to the right, or the element to the right, minus the cell we're on. So HP of -1c plus 1, that's our element to the right, minus the cell value we have, and 1. Okay, and again, in this case, here we'd be comparing kind of what's -5, or sorry, yeah, -5 6 minus 30, which is negative 24, but we're checking that against the 1 because, or not checking it against 1, but we're checking to see if that's negative. And if it is, then we're just going to use or if it's 0 or negative. If it is, then we're going to run with the 1. Otherwise, we'll say L if the cell is less than or equal to 0, HP of negative 1C is going to equal whatever we had to the right of us, which was HP of, I guess, negative 1, C plus 1, plus the absolute value of the cell. I'm going to move this over just a touch more, give us a bit more space. So we filled in the bottom row and the rightmost column. The logic here for this final piece is going to be very similar. I know I can kind of piece this all together into one line like I did here in a ternary statement. We could maybe do that at the end. I also know that these could be else statements. The reason I've left it like this though is just as I'm walking through the logic, it's a bit easier for me to keep my brain on it. And hopefully when you guys are watching, maybe it'll help you understand it just a bit better if you can see the logic fully spelled out. Now we actually want to say for R in the range of, and we're going to start with, we'll start with the second last row and the second last column, right? So we're going to start with kind of with this, with kind of this piece right over here, this cell here. And so this is going to be in the range of same thing. We'll have the length of HP minus 2, and we're going to go one row at a time. And same thing with the columns. For C in range, length of HP at the given row, minus 2, minus 1, minus 1. So I'm going to say the same thing. I'll say cell is equal to dungeon of RC. Okay. If the cell is greater than 0, we're going to need to do the following. And we're going to say that HP of RC is going to equal, let's see here. So we said that we're going to take the max of some calculation and 1. Okay, so just like we've been doing here, we know that, so I'm going to make a bit of space here. We've been taking the maximum of some calculation, kind of one of these two numbers and 1. Rather, one of these two numbers minus cell. Okay, so we're going to have some number here that we're going to subtract this positive cell value from. And, you know, if that gets us to negative for whatever reason, we're going to keep it at 1, and it's almost bounded from the floor up. So what are we actually interested in here? Well, let's think about how we actually tackled this problem when we looked at it. We said that for me to kind of get anywhere, I would need to take the value that I have right here and compare it to what's on my right and what's below me, right? We compared the value to the right and the value below. And again, I'm looking at my notes here just because I don't want to mislead you guys here. But what we did was we said we're interested in finding the lower of these two values. Rather, I think I'm highlighting here, but what I should be highlighting is this value right over here, okay? If I'm sitting at this cell right over here, I'm interested in looking at the lower of these two values, right? Because that's where I'm going to want to make my move. We're trying to solve the optimal minimum substructure. So to do this, I'm going to take the minimum of my left and right, or sorry, right and down. So I've just written them out right and down just as jargon almost. I'll move this up a bit, only to kind of illustrate a point here. But the cell to the right of us is going to be HP of, it's going to be in the same row, so R but C plus 1, whereas the cell below us is going to be HP of R plus 1 in the exact same column. And so the logic I'm doing here is exactly the same like what I did up here and down here. It's just that I need to compare the minimum of the value to the right and below me right now. Finally, if cell is less than or equal to 0, we're going to say that HP of RC is going to equal what? Well, it's going to equal, we're going to have to take the minimum, again, of the two values. So maybe I'll copy and paste this over. The minimum of these two values. And then to the minimum of that, I'm going to have to add the absolute value of the cell that I'm sitting at right now, exactly how I did right here. And that logic should be just enough to actually get us through. I'm going to press run to make sure I didn't make any of the mistakes. And I think this might be 2 videos in a row where I actually get it all on the first try. Wicked. So it's, as you can see, we get this in a pretty high percentile. You can definitely speed this up a bit by changing these to else statements instead of elif. I'm going to leave it just for you guys, just so again you can see the logic for yourselves. There may also be a clever way. You know, let's say you had a very big table. You had a big 2D table. At any given point, do we need to store this whole table? So I think the answer is yes. I'm almost thinking aloud here on how we can improve the space complexity. If you guys have a good idea of how to do it, let me know down below, because I don't have anything that's coming to mind right now in terms of how we can maybe potentially save less data. But I think you could probably do this with only 2 rows. I think maybe instead of saving the whole table, you can store 2 rows at a time and almost work your way upwards. And you'd have to do a bit of error checking on when you're comparing your right and below to make sure you're not going out of bounds. But either way, it is what it is. I hope you guys enjoyed it. I hope you found it helpful. As always, let me know in the comments down below if you have any questions, and I will see you guys next time. Peace.